Hello, everyone. I'm Shoichi Teshima from AngleTry Associates, Japan. My presentation is predictive maintenance of escalator using MT method. Just a moment. I presented our research on earthquake prediction at ICRQE 2021. At that time, I commented on the following 2 points. Those points are presented by Dr. Taguchi. The process of for earthquake prediction is the same as for predictive maintenance of plant and equipment. The important issue is what to measure for the purpose. In earthquake prediction, we used movements of electronic reference points obtained by GPS. The data used in this study are current waveforms obtained from the motor of an escalator. This is the item in this presentation. Just a moment. This diagram shows the escalator structure. Steps, belts, and some internal structures are also shown. The drive motor and gear unit are located here. Motors are usually AC motors, but sometimes DC motors are used. There are many causes of escalator trouble. For example, objects may get stuck in the step, while the motor or drive components may wear out. It is known that those troubles appear in the motor current waveform. This is an example of normal AC current. Slightly deformed, but within normal ranges. This is not normal waveform. As you will understand, it is difficult to judge how much deformation is a sign of failure. Therefore, I considered it appropriate to apply the following procedure. Collect conditions that inspectors judge to be normal. The normality of the object is quantified on this basis, and if the value is over the threshold, it is considered a sign of failure. Apply MT method for the quantification. Now, let's review the concept of the MT method. The MT method defines the normal group as the unit space and uses the Mahalanobis distance to determine whether it is normal or not normal. The unit space can be represented by a network called the correlation ball made by the normal group. The circles are the input items and the lines are the correlation coefficients between the items. The Mahalanobis distance is the distance from this center of correlation ball. The mathematical formula for the empty method is given here. If you'd like to know more details, please see the references at the end of the proceedings. Next, I explain how to obtain the features from waveforms. Dr. Taguchi proposed a unique and powerful feature extraction method in 1995. First, draw several horizontal lines on the wave. Then count the intersections, 1, 2, 3, 4, and so on. Intersection and amount of existence. These features include information on frequency, amplitude, and waveform shape. This is simple but very powerful effect. I devised new feature values using this idea. It is for quantify the shape information of the waveform. What do you think these three mountain shapes can be quantified in order to distinguish between them? First, define a rectangle around the mountain and draw several horizontal lines. These horizontal lines are called reference lines. For each line, the start length is defined as the length from the left edge of the frame to the point where it hits the mountain. The other side is defined as the end length. The corresponding values are given next to each line. The corresponding values. This group of values is the mountain shape information. This idea has been patented in Japan. Now that the quantification has been done, the next step is to apply the empty method. These graphs of dozens of waveforms overlaid. This one is normal, this one targeted, including abnormal. The normal waveform is homogeneous, although there is some variation. We have developed software to perform feature extraction and empty method analysis. This is the screen. First, define a red area on the three mountains with 10 reference lines each, and find the start and end length from each reference line. Ten normal waveforms are used as the unit space and calculate the Mahalanobis distance for the target data. In this diagram, the green line is representative waveform of the 10 unit spaces. The blue line is the target waveform. The MD of this target waveform was 2.3. The value is small, so judged to be normal. The next example is judged abnormal due to the large MD. In this case, MD is over 17. Threshold is set at 4. Also, as you know, the empty method has a causal diagnostic function. This means that it is possible to know which features are the cause of the anomaly. The software shows the item, that is the feature number, and the vertical axis shows the contribution to the anomaly. If you place the cursor on the highest bar, the corresponding reference line is shown in red. The following example is also judged abnormal. MD is over 6,000. The cause is the height is low. Height is low. If such low height doesn't exist in normal waveforms, the MD becomes such large value. This graph summarizes MD for several waveforms. The first 10 are judged normal by the inspector. The MD has a small value. These are waveforms not used in the unit space. From the 11th, they are abnormal and consistent with the inspector's judgment. Thus, it was found that anomalies can be detected from the motor current waveform. This graph shows the empty transition model in predictive maintenance. When MDs start to grow, we can prepare the escalator for inspection. Cause diagnostics will also help us to know where to inspect. As indicated by this green line, serious problems can be prevented. Next, I will explain predictive maintenance in the case of DC motor. This graph shows the current waveform when the DC motor starts to move. From here, start to move. No persons are on board at this time. People are not on board yet. It is known that engineer can judge anomalies from this curve. This waveform is normal. There is a slight overshoot after the current rises and stabilizes at a constant current. Engineers can tell if there is some trouble, if there is slow starting or a lot of overshooting. This graph shows the results of Mahalanobis distance for various waveforms. The first 5 waveforms are normal, but after them are almost abnormal. Some waveforms and Mahalanobis distances are shown. The MD of this waveform is 0.8 and is judged to be normal. The next waveform showed MD to be quite large. (12^10). The overshoot, this is normal, this is target. The overshoot is large relative to the green normal waveform. Probably normal waveform would never reach this height. In such a case, there may be an abnormality in the clutch section that transmits rotation. This example has MD is 85 and is judged as abnormal. You can see that the rise of the waveform is slow. Cause diagnostics indicates that the rise of the waveform is beginning to slow relative to normal in this part. The motor load may be starting to increase even though there are no people on the escalator. The next example has an MDE of 62. As in the previous example, the rise is slow. However, compared to the previous waveform, the degree is smaller, and we can agree that the MD is also smaller. The former waveform and next waveform. MD is 85, MD is 62. This is normal since MD is 3.6. This is MD is 45. which indicates that something is different from the normal waveform. Diagnosis of the cause shows that the rise is faster from this red line. We introduced the possibility of predictive maintenance of escalators by constantly monitoring motor current waveform. In today's case, the rule of thumb is that the signs of abnormality are pronounced in the motor current, so predictive maintenance can be performed only on the current waveform. From motor current, we get current and feature extraction and make unit space and analyze Mahalanobis distance. In general, facilities and equipment monitoring uses multiple measurements for monitoring. In such cases, the feature extraction and empty methods can be applied in exactly the same way. By the way, I think you are interested in deep learning. Its abilities are expected to have unlimited potential. Recently, the possibility of ASI, not American Supplier Institute, this case, artificial super intelligence, an AI that is 10,000 times more capable than the human brain, has also been a topic of discussion. However, I believe MT is easier to use and more reliable than deep learning for technical issues. There are several reasons, but I will mention 2 points. The first point, Dr. Taguchi proposed the feature extraction discussed here. It is a characterization technique, featuring technique that no one has thought of, but that we can understand. Which is better, the MT that engineer can understand, or a deep learning that we cannot understand the process? Deep learning also performs feature extraction during the training process, but the technical significance is unclear. It's black box. Second, MT requires very little data for training. In the case studies presented here, the training data was only 10 waveforms. Dr. Taguchi stated that engineers required to prediction ability. The MT method is the easy to use and powerful prediction method he left behind. I conclude my presentation by expressing my deepest thankfulness to Dr. Mahalanobis and Dr. Taguchi. That's all for my presentation. Thank you for uh, for your attention. Bye-bye.